Hi everyone, my name is Daniel Lindau and I'm working as an identity specialist at Curity. In this session I will talk to you about OAuth for mobile applications, the seventh part of our Getting Started with OAuth and OpenID Connect series. And this is the agenda for today. I'm going to start off with doing a quick recap of the OAuth authorization code flow, and then I will explain the difference between public and private clients. We're going to talk about how to use OAuth best practices to achieve single sign-on between your application and the system browser and also other apps in the same device. Next, I will talk to you about what PKCE is and the problem it solves. And lastly, I'll show you a technique you can use to create unique client instances that also is tied to a user using dynamic client registration. First, a recap of the OAuth authorization code flow. It's good to have a fresh memory of that since we'll extend it a little bit to fit the mobile applications. In the code flow we have four different actors: the resource owner, a user, a resource server, which is the API, a client, and an authorization server. The resource owner is a user of the client application and owns some data in the resource server, which it wants to allow the client to access on its behalf. To allow that delegation of access to happen, we have the authorization server to issue tokens as proof that the resource owner allowed the access to be delegated. So to start off this delegation process, the resource owner typically opens up the applications in a web browser and press a button to link my account or log in or something similar. Pressing this button will redirect the browser to the authorized endpoint of the authorization server, performing an authorization request. To accept the authorization request, the AS has to know the user is. Since it usually can't perform authentication on its own, the AS sends the user to the authentication service for authentication. The authentication service then authenticates the user by some method available and returns the result to the AS. When the AS has received the response, it will know who the user is and can now decide how and where to respond. In some cases, the AS first asks the user for consent before it can issue the response to the client. The response is an HTTP redirect to a pre-configured URL, pointing to the backend part of the client. A code is appended to the redirect URL, which should be used as a one-time password to exchange for actual tokens. This code can be used to obtain tokens using the back channel. The client can now do a token request using its pre-provisioned credentials and the code it just received. If the AS can authenticate the client from the token request, it can issue tokens that represents that the resource owner accepted that the client could access the data on their behalf. In this case, the AS also issues a refresh token to the client. Usually the access token has a short lifetime, and the refresh token can be used to obtain new access tokens without involving the user again. Thus, it's a very powerful token and should be treated with care. So that's the code flow recap. One thing to note from this flow was that the client had to authenticate to the token endpoint to be able to make the token request. This means that the client has to be given a credential of some sort, which might be easy with some clients, but a lot harder for other clients. This leads us into the next topic, the client types. There's two client types in OAuth: the public clients that can't be trusted a secret and the private clients that can. The typical private client is a web application with a backend. A credential can be given to the application in some way, and the credential can be stored in the backend and never be exposed to the front end. The only time the secret will flow is when performing the token request, which will be made using a TLS connection. An example of a public client would be the single-page application. The full client is in the browser, so there's no way of securely distributing a credential to this client. And if we could, it would be very hard to keep it secret. So the SPA is definitely a public client. The mobile client is a bit of a hybrid. It does the job of keeping secrets pretty well, but the hard part is to give it to them. The nature of the app is that it contains its own front and back channel, so each instance would have to have access to the credential. This will essentially make it so that the credential will have to be distributed with the app binary and can be more or less be considered public information. For this reason, we consider the mobile app a public client. Later in this session, we'll look into making the situation a bit better for the app. Now, let's have a look how a code flow would look when we are using a public mobile application. This is almost the same picture as before, except that the backend is part of the client is switched to be a mobile device, representing the app. We can imagine the client having a front-end channel being a browser component and a backend being the app, where it's able to execute requests separate from the front-end channel. When we're talking about these types of applications, it's very important that a system browser component is used to make up the front-end channel. There are different components for the different platforms that can be used, but you can also use the default browser device to make the authorization requests. And why do I think it's important to use the system browser component? Well, first of all, using a browser decouples the authentication method from the app, so the authentication method can be updated server-side without having to create new app releases. Using a system browser component also gives you access to the shared cookie jar. This will enable the possibility for a single sign-on between apps on the same device and the system browser. This is made possible since the authentication service can set cookies to remember the user, and since the same cookies are available to the users of the system browser, the user won't have to log in more times than necessary. Also, these components does not give the app access to what's happening inside the browser, effectively blocking the possibility of collecting user credentials. This is giving the user a high level of privacy, and the users can be more confident in entering their credentials. Let's get back to the flow. Now that we decided that the app is a public client and we have a front-end channel that's sharing cookies with the system browser, to start the flow, the user clicks a button in the app and a browser component pops up. This browser component performs the same GET request as before. The AS redirects the browser to the authentication service, which will proceed to authenticate the user. During authentication, the authentication service has the possibility to set and read cookies to be able to reuse the authentication result at a later stage. Because of that, when we try the same flow again, using this app or another one in the same device, we could achieve single sign-on. When authentication is done, the AS gets the result and can issue the response to the client. The response is pretty much the same as before, but with a slight difference. The redirect URL is not pointing towards a HTTPS backend URL, but to a custom protocol. Our app is registered to handle this protocol and will be triggered when the browser component sees this redirect. When the app is triggered, it can close the browser component and proceed to redeem the code. After the browser component is closed, it can make the token request. This token request is slightly different since the app is categorized as public and haven't been trusted with a secret, so the token request won't contain a client secret. The AS can then validate that the code is valid and that it has been issued to the client ID that was presented in the token request. If the request was valid, the AS can issue the access token. Note that a refresh token could be issued, but it's not recommended since the client is public and cannot be trusted with such a powerful token. We can see two distinct problems in this flow. The client is never authenticated, it merely identifies itself with a client ID that is publicly known. As a consequence, the level of trust for this app should be considered very low. And also, since the way to switch context from the browser to the app is by using a redirect to a specific protocol, and that protocol could be registered by any app on the device, we're open for a code interception attack. If everything goes as expected, the response from the AS would be a redirect that triggers our app. But if a malicious app installed the same device has registered the same protocol, it could be that the malicious app gets the trigger instead, and also gets the code. Since the malicious app now has a code and the client ID is publicly known, it can easily change the code for an access token and start acting as the real app. We need a way for the AS to know that the one requesting the token is the same entity that the code was issued for, which leads us into the proof key for code exchange, or PKCE for short. PKCE is an extension of the code flow to add in a proof of possession key to the authorization and token requests. In short, the PKCE procedure requires the client to generate a random key for each code flow and use it in both requests to prove that it's the same client making both of the requests. Let's look at it in detail. Here, the client has generated a key and adds on two new parameters to the authorization request. The code challenge, which is a hashed version of the generated key, and the code challenge method, which is the method used to hash the key. The AS can make note of the hashed key and method and can then proceed to issue a code for the client. When the app has received the code, it can perform the token request with an additional parameter, the code verifier, which is the clear text key the app generated. The AS can then hash the code verifier using the method that was presented in the authorization request and compare the result with the code challenge presented. If the result matches and the code is valid, the AS can issue a token for the client, since it proved that it's the same client that initiated the flow. If the malicious app was to get a hold of the code, it cannot exchange the code for a token, since it has no way of obtaining the code verifier to present to the AS. So PKCE has now mitigated against the code interception attack. The AS can be sure that the client initiating the flow is the one fulfilling it, but it still haven't proven to be a trusted client, just that it's a client that knows how to do PKCE. This might be enough when the client is a pure browser client, since we have mechanisms in place to make sure that the origin of the request come from trusted domains, such as CORS and CSP. But for the mobile applications, we don't have that. To further raise the trust level of the app, we need to add additional methods. To do this, we're going to use dynamic client registration and tying the registered client to a resource owner. Travis has previously talked about DCR in this series, so I'm not going into details here, but the outline of the protocol is this. The unregistered client obtains a registered token in some way and uses it to post a JSON document containing its configuration to the register endpoint of the AS. The AS can then validate the token and respond with a success message containing a client ID and a client secret that the client can now use to perform the actual flows. For mobile, we will use a flow where the user is authenticated to obtain the registration token. In that way, we can tie the resulting client instance to a user that's authenticated. To obtain the registered token, the app will have to perform an authorization request with a specific scope of DCR. The AS will ask for authentication as usual and return the response to the redirect URL. In this case, I used implicit flow, so the response contains the DCR scoped access token directly. This token can then be used to post a JSON document containing the configuration of the client. The AS can now validate the token and the body presented and create a new client instance that uses the configuration that was asked for in the JSON body, if those settings are allowed. The AS generates a new set of credentials which uniquely identifies this client. These credentials can be used in upcoming code flows to be able to obtain tokens. The server can trust this application at a high level, even though the origin is a public client used to register. It can do so since this is now a unique instance, making the attack surface a lot smaller. Also, since the user is authenticated during the registration process, the user has a chance to say whether or not it trusts the app. This app instance is now traceable in logs, and there could be user interfaces for a user to see which instances it has created, and even revoke certain clients. Since the mobile platforms is generally good at keeping secrets after receiving them, the client might now be trusted with a refresh token since it can authenticate with the credentials received. And that concludes this session. To summarize, in this session I explained how you can use a system browser component to perform your authorization request to raise the level of privacy and get SSO for your local apps. We talked about how PKCE is a mechanism for public clients to not allow third parties to steal access tokens by redeeming your authorization code. I showed you a technique that can be used to create unique instances of your app to achieve high trust and make it easier to trace and revoke unused or unwanted clients. As a last remark, check out the best practices RFC called OAuth 2 for native applications. A lot of the things I talked about is expanded on there, and it's a good document in general. Thank you for listening, and please check out our website for upcoming sessions and lots of materials regarding OAuth and OpenID Connect. Thanks.